So hi everyone, welcome to the last lecture. And today I just kind of wanted to take a step back and kind of get an overview of what we have done and what we have learned and principles that we can take through life now that we, are post CS 466, right? So, all right, so this is what we're going to talk about today. So we're going to first see like a course overview and recap, just so that we can refresh everything that we have learned. And then where do we go from here, right? So, all right. So what was this course about? So in your previous algorithms and optimization data structures courses, like what did you learn? You learned some combinatorial techniques, right? So you learned before divide and conquer, greedy algorithms, dynamic programming, local search, etc. And you also learned about a bunch about data structures, right? Like heaps and balanced trees, etc. And the techniques above, like that, were probably not discussed in as much detail as we had right now. They emphasize mostly two computational models, right? Sequential and deterministic computation and the query model. And well, for some of you, you also saw some randomized, right? In the randomized quicksort, for example, you also saw already some randomized computation, right? But mostly we had those two computational models. And in this course, what did we do, right? So we used the algorithmic lens. So, and what is the algorithmic lens? It's to see kind of the computational side of every problem, right? So every problem has a computational facet to it. And we use this algorithmic lens to explore several models of computation. So, and what were the models that we talked about? So we talked about deterministic sequential algorithms, randomized sequential algorithms, randomized parallel algorithms, right, with the isolation lemma, for example, sublinear time algorithms, and also we have memory constraint algorithms, right, which was the streaming, for example. And we also had distributed algorithms. We also had online algorithms, right, where we learned the competitive analysis. And we also saw some algebraic algorithms, which are more like the matrix multiplication. And also we saw interactive models of computation, right, with zero knowledge proofs and probabilistic checkable proofs, right? So you can see that we learned quite a bunch of a lot of different models of computation. And we also expanded, not only saw different models of computation, but we expanded your algorithmic toolkit. So now you're more powerful, you have more tools to solve problems. And now, what did we learn? Well, we learned amortized analysis, for example. We learned how to use randomness in algorithms to obtain like much faster algorithms. And we learned concentration inequalities, which are key to the random processes that are underlying the randomized algorithms, right? So these are the concentration inequalities are the things that allow us to say, oh, we're always going to run close to the expected running time, or that, the expected cost of something that we have, like it is concentrated, right? And then we also learn how to deal with NP-complete problems, right? By using approximation algorithms, which are well beyond the combinatorial approximation algorithms that you may have learned in previous classes, right, with integer and semi-definite programming relaxations. And we also learned about hardness of approximation to explore the limits of approximation algorithms, right? So these are things that we learned in this course. And now I want to talk about what were the high-level principles underlying pretty much every lecture or every new topic that we learned, right? So what did we learn in a high level? Well, whenever we encounter an algorithmic problem now, what do we need to do? We need to just follow this template. The first question we should always ask is, what model of computation is most suitable for this problem, right? Because the same problem actually can have many models of computation for which is very suitable, and those can have application in different areas, right? Because sometimes you can have the same problem, but then you can ask, well, but what are my algorithms? Can I use distributed algorithms, or do I need to solve this problem in one computer, for example, right? So the same problem can actually be applicable in two different models of computation. So you need to keep the model of computation in mind. And what do I mean by which model is most suitable, right? So here we're asking, what are the most important resources and constraints that we need to respect in order to solve the problem, right? So what are the principal constraints that we need in order to solve the problem? And that will pretty much tell you what model of computation is most suitable, right? And the second one is, once we settle on the model of computation, then you can say, okay, now I know my constraints and the resources I have. And once I know that, what we would like to know is, well, what guarantees are even possible in this model of computation, right? What are some things that we can hope to compute, or what are questions that we can hope to answer, right? And the question could be, for example, can we hope to get an optimal answer to the problem? Right? And if you remember, like even in the streaming model, there are many algorithms that it's impossible to get optimal results. So we have to settle for some approximations, right? So, and sometimes even the problem is completely impossible depending on the assumptions that you're making. You need to change the assumptions, as we saw in the, for example, in the consensus problem with an arbitrary number of failures, right? So that we could never solve that problem, right? So we know there are some impossibility results. Okay. So, all right. So then once we know what guarantees are possible for this model of computation, what we want to do is, well, okay, what is the simplest, what is the most natural algorithm to solve it? And what is its complexity? Can we just analyze the simplest and most natural algorithm, right? Or in particular, what we also did quite often is, like, here is there a simplification of the problem which we can solve, right? So for example, if you remember the multiplicative weights update, what we saw is like, oh, what if I had one expert that was always right? And that kind of helped us in guiding to, like, in trying to find an algorithm that worked for that particular setting. And once we saw, it's like, oh, okay, like we can easily and oftentimes what happens is that you can often modify the algorithm that you found for the simplest setting to actually become a more general algorithm, right? And then the analysis, like, well, the analysis becomes a little more complex, but you also know how to do it. Does that make sense? So, so that's good, right? Like simplification can be here, like either more assumptions on the problem, right? Or, you know, like more or simpler cases, right? Like in a sense, like simpler, smaller examples. Let me say smaller examples, right? And then once we have those three, what do we do? Well, then the question comes, oh, can we do better, right? And better here will be, you know, either like faster algorithm or like less resources in general, right? Like what we want. Can we use less resources to solve it? Or, well, you know, can we have a more general algorithm, right? Because maybe if we have like, you know, if once we have a simplest algorithm to solve it, then okay, you're solving the full problem. So you would want like a faster, less resources algorithm. Or if you have an algorithm for a simpler problem, can we get a more general algorithm that works, right? And then the question becomes, okay, can we do better, right? Can we find a better algorithm? And now, once you try this problem a little bit, right? So we found a good algorithm. Once we found a good algorithm, you will still want to think, oh, can I still do better, right? That's always the question that's always there. And now, how do you kind of try to put this question to rest, the can I do better question, right? Is studying the hardness of the problem. Oh, is the problem hard? So certain problems, as we saw, like for the traveling salesman problem, they're really hard to even approximate, right? So if the simplest algorithm is a really bad algorithm, it's like is a brute force algorithm, then you start wondering, okay, is this problem actually hard? Right? And by hard here, we can mean like NP hard or any other complexity class. And the question is, if it is hard, if the simplest algorithm that we can find is only exponential time, let's say, can we hope to relax the guarantees, right? Now, this can have, as we discussed before, this can have actually two different connotations. One is, oh, is the problem like, do I only have a brute force algorithm, in which case we want to have approximation algorithms? And one thing that we did not discuss in class is, what if I have an algorithm that is like, the running time is n to the 20, right, for problems of size n? Like, oh, I most likely cannot run this like practically. So then what you would like to do is, even in this case, you would like to relax the guarantees so that maybe we can get a nearly linear algorithm or an algorithm that runs in quadratic time and so on. Does that make sense? So maybe, yeah, it's worth writing it here, right? So if like only no kind of brute force algorithm, like, can we show NP hardness? And if so, then we want to have like approximation algorithms, right? But you know, if we have like polynomial time algorithm, but slow, like say, like for example, n to the 20, as we're talking about, like still like could be good to relax the guarantees, right? If we want in the end a nearly linear algorithm. Does that make sense? All right, and then once we established a little bit on the hardness of the problem, what do we have, right? We have an upper bound, which is an algorithm that you found, like you found a natural algorithm for the problem, and that gives you, oh, I can certainly solve it in this amount of time or with this amount of resources. And then if you establish the hardness of the problem, you will have a result, oh, no algorithm can do better than this much. And then you will have usually a gap. And then the idea is always to try to close this gap, right? Of can we do better or not? Does that make sense? All right. So then this is the template that we're going to follow, and then the ultimate point, right? Once we have this gap, is step 7 is, can we show that our algorithm is the best, right? So, and what is the idea? Well, what we would like to know is like, could we try to reduce the problem that we have to another problem which is known to be optimal? And by known to be optimum here is we usually need certain complexity assumptions, right? So, and this is something that we didn't discuss here, but you know, if you all would like to learn more about it, like you can look at complexity courses where, you know, there is a very cool field which is kind of recently emerged, like in the last 10 years, which talks about fine-grained complexity, okay, which is the study that under some complexity assumptions, and these complexity assumptions are called like the exponential time hypothesis or strongly exponential time hypothesis, okay, they prove that certain problems, you know, like added distance of strings and certain very like really natural problems, really practical problems, the algorithms that we have for them are essentially optimal under these assumptions, right? So, and this is something for you to learn, like further exploration here, like in the further exploration. Does that make sense? But this is kind of a template that, you know, no matter where you go and work, you know, once you're going to get a computational problem, now you know that you can follow this template, right? And you have tools to deal with every step along the way. Even up to step 7, but step 7, you may need more tools, right? That we didn't talk about in class. So far, so good? Okay. So here's an example, right? Let's see an example of this template. So in data structures, we remember that oftentimes one cares about worst case per query, and that's kind of what you learned before this course, right? Because, you know, this is usually how, for example, the internet's client server model is, right? Like the server is really trying to minimize like the situation for the worst, like the worst situation for any client, right? Like you want all the queries to be answered fast. But sometimes we don't care about worst case per query, but we care about worst case overall, right? And for example, if we use a data structure for sequential algorithms, which has been used quite successfully, even recently in solving linear systems. So like this is not something that's very old only. Like this idea here has been very successful. Recently, in solving like linear program solvers, like they're getting much faster linear program solvers. They're also getting Laplacian systems, like linear system solvers. And many more, okay? So the use of data structure in sequential algorithms to speed them up has been even very successful recently, and has also been like, and this is very old, right? So this is quite old, like quite an old application. Like back to the 70s and 80s, right? So, you know, so sometimes like we know now that if we don't care about the worst case per query, but the worst case overall, then we have more freedom to develop data structures, right? And with this freedom, what do we get? So what did we learn? We learned how to use amortized analysis to provide a better overall guarantee, right? And for that, we also learned 3 tools. What are the tools that we learned? Well, there's the vanilla amortization, which is just saying, oh, it's really easy to count the cost at every step. So I'm just going to account for the cost of the operation at each step, and then I take the average. And that's the vanilla amortization, right? That would be the simplest thing that you could do. But then we also saw different examples where it's really hard to kind of keep track of the cost of every single operation. But then we came up with some mathematical ways of actually upper bounding this, right? And one of them, which was really natural, was the charging scheme that I assign charges to operations. And these charges, all I know is that they kind of build credit, right? So if I assign a charge, initially the cost of the operations is kind of small, and then I build a certain credit, and then later on, whenever I have an expensive operation, it means I have to prove that whenever I have an expensive operation, I have enough credit that pays for this extra expensive operation, right? And if you remember, like when we increased the counter, for example, what did we do, right? Like the binary counter. All we did was like, oh, okay, let's charge 2 for each bit, because we charge 1 for the cost that we're currently charging for this bit. And the other one we save for whenever we have to flip a bunch of bits, right? Like because of the carrying operations, right? So this charging scheme was quite useful to just simplify the analysis of this algorithm. So it's a great technique. And the ultimate technique here was the potential function, right? That we assign actually charges and potential to the data structure itself, right? And we say, okay, now the configuration of the data structure has a certain potential. And then what do we need to argue is that if there is an expensive operation, then the potential will also drop by a lot and it pays for it, right? So the potential of your data structure is what is giving you the credit, right? So these were in order of generality. And right, so this is an example of that template that we're talking about, right? So what was the template? First, we identified the computational model, And what was the computational model? Well, the computational model is here. We're saying, oh, you know what? We don't care about worst case per query. We care about worst case overall. So that already tells us that our goal is very different, right? And then naturally you can see that a new technique, amortized analysis, arises, right? And then all we need is we learn different tools to deal with it, and then we can analyze it and kind of try to prove optimality, right? So that's what we did for amortized analysis. And another example, which the computational model was quite important, right, is when we have like the input comes to you in a similar way, but then even then you have to consider different models, right? Because think about it, when the input comes to you online, right? And what do we mean by online? It comes as a stream of events, right? It comes as a sequence of events, and you have the setting of YOLO, right? Like you only look once, right? So even in this setting, we may have different computational models and computational goals. And what are those? Well, even here, so we learned in the data streaming, if memory is your main constraint, then you're in the data streaming model, right? That the data is going to come to you, but you don't have what you really want to preserve is the amount of memory you use, right? And here we're content with approximation of the best answer, right? And here we saw some examples, like some that are impossible and some that are possible, like for example, computing the median or heavy hitters or the number of distinct elements, right? So, and we saw how to compute the heavy hitters and distinct elements. And, but then we also learned that, okay, what if the objective is we have enough memory, we have as much memory as we want, but the idea, the main problem is that we want fast updates because every time the data comes, we need to decide to make a decision on the spot, right? Without seeing the entire input. So what's the idea? So then we're in the setting of online algorithms, right? That we want fast updates because we need to make a decision as the data is coming. And then here, what actually makes sense is to do as best as we can compared to the best in hindsight algorithm, right? Because now here we have all the resources, but the only thing is that we need to keep making decisions. And in the end, what we realize is that the types of questions is not that we have an approximation of the best answer, right? But what actually makes sense is to do as best as we can compared to the best algorithm that could see the entire input. And that would be the golden goal, right? So instead of having a best answer, we may never be able to get close to a best answer, but what we can do is we can just compare ourselves to algorithms that can see the entire input, right? So you can see how those different models will give you different goals, right? And this already gave rise to the competitive analysis that we studied, right? And here we have many like examples, right? So for example, when we saw the multiplicative weights update is an example of online algorithm. And the paging problem that we saw as well was the kind of main first example of online algorithms, right? So, all right. And then in addition to that, we also learned that randomness gives us power, right? Which at first is a little bit unintuitive, right? And so we learned in this class how to use randomness in algorithms. And to use randomness, we also learned that we have to do a trade-off. Like with deterministic algorithms and worst case analysis, we knew that our algorithm should be correct all the time. But when we use randomness for every input, what are we going to do? The only requirement that we need is that the algorithm works most of the time, right? So we trade this all the time with the deterministic. We say, oh, most of the time algorithm will be correct and I'm content with that, right? But I want like a faster algorithm or, you know, a polynomial time algorithm. Does that make sense? Okay. And then, well, and we also saw that this is quite useful in many settings, right? So what are these settings where randomness is useful? Well, one setting is really when we don't know what to do, right, deterministically, then we definitely need to use randomness just to make sure that we get somewhere, right? And also a different setting than the when we don't know what to do is when the problem has some adversarial input format, right? So remember, if we're in, let's say, an interactive setting, as we saw, of probabilistic checkable proofs or some, when we're in this setting that we are able to pick a random bit and give to the adversary, and then the adversary will have to respond to us, like the prover can respond to us, right? So we're able to deal with dishonest provers because the prover won't know what we're going to ask, right? So we can use randomness to cope with adversaries. Does that make sense? So you can see that randomness is not only useful to give us some faster algorithms, but also sometimes they're kind of inherent in the way, in the setting of the problem, right? Especially in the interactive proofs, like randomness is really necessary. Otherwise, things are impossible, right? So, all right. And what else? And where else is randomness useful is another settings when we have to make decisions before seeing the whole input, right? Like the streaming model, for example, we pick a hash, like a random hash function, and then we're able to hash the elements and then kind of use very little memory to extract some information about the whole stream, right? So, all right. And what other ways is randomness really useful? Well, the other ways are when a problem can be encoded in the algebraic format, then we know that we can use polynomial identity testing or those fingerprinting techniques to solve the problem really fast, right? And we saw that, for example, for perfect matching. And another setting is when we need to construct objects which are abundant, but really hard to construct, right? Like, so, and, when does this happen? Well, this happens, for example, when we have hash functions, right? We want to construct some objects that are abundant, but they're really hard to construct. And then we just say, okay, let's pick a random function from a family of hash functions, and this will work for our input, right? But it's really hard to construct deterministically one, right? Like even when we saw, for example, the perfect hashing, even when we know what the entire data looks like, it's still really hard to construct a perfect hash function for that, right? So we use randomness to construct those. And in graph specification as well, if you remember, we have a graph and we want to find a sparser graph that preserves all the cuts. What did we see? Well, we saw that we don't know how to construct it deterministically, but if we pick edges with certain probabilities, we obtain a sparser graph with the same property, the same cut properties, right? And this also happens in dimension reduction, which we didn't see in class, and in constructing certain graphs that really expand, and these are called expander graphs. Okay, they're quite important in computer science and combinatorics. Okay, and all right, and the other one as well, which was really great application that we saw where randomness was useful, is when we need to estimate the number of objects which are hard to count. Okay, so if there are certain objects that are hard to count, you can use random walks to essentially count the number of those objects. Okay, and that we didn't see an application of this in class, right? This is a potential kind of final project, right, for Monte Carlo for approximating the permanent. Okay, so randomness is quite useful there, but we also saw that these random walks are quite useful for us to estimate many things related to random walks, right? They appear everywhere. And you can even think of randomized algorithms somehow as doing random walks as well. Okay. So, all right. And what is the last setting that I want to say that randomness gives us power is in approximation algorithms, right? So as we saw, there are certain rounding procedures that we don't really know how to do deterministically, right? And when we don't know how to round things deterministically, we can actually use a linear program, take the solution, interpret that solution as a probability distribution, and be able to round the solution randomly using the answer to the linear program as our guiding probability distribution, right? So that was something that was quite cool that we saw. All right, and then what was something else that we saw in class is how to deal with NP-hard problems, right? So when we're faced with NP-hard problems, like let's say optimization problems, we still want to solve them as best as we can. And now to that task, it's important to relax the guarantees, right? Because of course we're in an NP-hard, so if we believe that P is not equal to NP, then what we want to do, or not only even if we believe, I think regardless of whether we believe or don't believe, is an NP-hard problem. A lot of people try to solve it. We can try to solve it as well, even if you believe that P is equal to NP, but in the meantime, you still want an algorithm for today. So, and maybe you may not care about the like optimal solution, but you want to get something close, right? So you can relax the guarantee and the problem becomes easier, right? So, and instead of trying to find the best solution, we just want a solution that's guaranteed to be close to best. Just so that you can say, oh, I have something that works quite well, and I want to prove that P is, even if you want to prove that P is equal to NP, you can just say, oh, I'm just going to use this algorithm now because I want the decision right now. And then I'm going to keep working on a better solution, right? So that's regardless of your belief. All right. And so what was the idea here? The idea was there's two approaches to dealing with NP-hard problems, which is we can formulate them as integer programs or quadratic programs, and then we can relax these problems to problems that we actually can solve, which is linear programs or semi-indefinite programs, right? And once we do that, then, and if these linear programs have enough structure, like we saw for the vertex cover, right, then deterministic methods are good. So we're able to round deterministically. But when integer programs have, and this is when like the integer program have nice vertex solutions. And that's what we saw in the exercise, exercise 1 of homework 4, I think, right? That the deterministic, or 3 or 4, that deterministic methods are good. And, but if the integer programs do not have nice vertex solutions, or we don't know how to prove them, then we use randomness to the rescue, right? That the solution of the linear program will kind of guide us to use randomness based on the solution to the linear program. All right. And so this is how we dealt with linear programs. And then we also learned that interaction can give us powers and limitations, right? So we learned how to see, like, complexity. We learn how to see certain complexity classes as proof systems, right? And what is a proof system? Is just an algorithmic way of checking like any validity of certain statements, right? If certain statements are true or not, right? And is a system, is any system that, given certain claims in the system, is a system that you devise, which is an algorithm that always is able to tell, given a claim, there's a proof, and it can evaluate whether this proof is correct or not, right? So that's what a proof system is. And then we learn about complexity of proofs, right? And how we can use interaction to actually give different characterizations of complexity class, right? And this was the concept of the PCP theorem, right? That we learned that PCP 1 log n was equal to NP, right? So this is interactive proofs are equal to like the NP. And so, and well, yeah, like NP can be characterized as problems that have proofs which can be verified by only making 3 random queries to the proof, right? And the proof is like really big, but you only need to check 3 bits of the proof, and you're able with high probability to detect whether the proof is correct or not. And we also saw that we can use interactive proofs to construct reductions which preserve a gap between the yes and no instances, right? So, and these reductions that go via PCP, they are like these special reductions allow us to prove hardness to approximate, right? Like the hardness of approximation. these gap reductions allows us to prove hardness of approximation of certain problems. And also, apart from this hardness of approximation, interaction is not only good for hardness of approximation, but we also saw how to use interactions to give zero knowledge proofs, which have huge applications in today's world in the internet, right? And the main idea of zero knowledge proof is that you want to convince someone that you know something or that you're telling the truth without revealing any knowledge on how you do it, right? Without revealing anything about the secret, so that you can always keep the secret safely, right? So, all right. And then we also learned a little bit about algebraic and arithmetic algorithms, right? So we learned about algebraic and arithmetic models of computation. And we saw, oh, if my problem is algebraic, right? Like I'm multiplying two matrices, for example, then this model is the most natural model to deal with. And it's widely used for some of the most used algorithms in real life. What are the two kind of most used algorithms in real life? Well, matrix multiplication and discrete Fourier transform are two of the top three algorithms that you'll ever use, right? Like sorting is probably the first one, and then those two come as second and third, right? So it's arguably very applicable, and is also widely used for design of parallel algorithms, since linear algebra can essentially be done in parallel, okay? This is something we didn't see in class, but if you'd like to see, there's a final project topic, which is like Berkovits theorem, which was a final project topic, but even if you're on a look at it, you can see in the references, or you can take a class in algebraic complexity theory, and they will teach you certainly this is a central result in algebraic complexity theory. And more generally, one thing that we didn't discuss, but which is also true, is that any polynomial we can compute in real life is actually a determinant. So determinants are essentially the only polynomials out there, okay? So because any polynomial that you can compute is a determinant of some matrix that's not that big, okay? So, and that's why this connection between kind of linear algebra can be done in parallel, because you can compute determinants quickly. And also, even if you're doing algebraic algorithms, you're actually computing certain determinants, okay? So, all right. And then after we saw algebraic computation, we also talked about distributed computation, right? And these are algorithms which ran on a network or multiprocessors within a computer that share memory. And what are the idea? What's the idea here, right? So they want to solve resource management problems, data management and transmission, synchronization, consensus, and many more problems. And what were the challenges in the setting that we had? Well, the challenges were that there's concurrent activity going on, and this is a challenge that we certainly didn't see in the previous models of computation, right? There was also uncertainty in the order of events, and there's also the idea of failure and recovery of processors with channels, right? The same way that my internet connection failed last time, right? And we saw that even within distributed computation, there's many models to consider based on the memory and communication types that you're going to allow or that you have, the timing of the processors in your network, and also the types of failures that you want to tolerate, right? And then now that we have this whole list, you may be wondering, oh, okay, why are we going through the whole list, right? The reason is, well, this is just a recap of all we learned in the course, and you can see that you learned a lot. So I'm very proud of all of you. And so now, why did we talk about all of those models, right? So the idea is, the question here is, well, we saw many different settings, like important problems and techniques. And you may be wondering, well, in this class, did I just learn a bunch of tricks, like to do with those things? And the answer is certainly not, right? And why is that? Well, we saw, for example, how randomness is applied in many different settings. And we saw that, it's not just a bunch of tricks, but we saw that all of these techniques that we learned, they're very common and appear in many, many areas, right? So in a sense, we didn't just learn a bunch of tricks. We learned that there are certain underlying principles, for example, in randomness, that these same underlying principles can be applied in many different settings, right? So what we learned is that there's a certain structure, a certain underlying structure, mathematical structure that can be applied in many areas, right? So for example, in hashing, fingerprinting, polynomial identity testing, right? So when we understand randomness a little bit more and probability, then we're able to apply this to many settings, right? We also saw how we can learn about interactive proofs, which is something that comes from proof complexity and has nothing to do kind of with algorithms, to proofs that certain algorithms cannot be approximated up to a certain point, right? So here we saw the connection between having small proofs for certain claims can actually help us in proving that certain algorithms cannot be approximated up to a certain point, right? So you can see here a connection between two different areas of complexity theory, well, in algorithms and complexity theory, right? That they're essentially intrinsically related. Because remember that the PCP theorem was also equivalent to a hardness of approximation statement, right? So in a sense, we didn't just learn a bunch of tricks, but we learned how algorithms and complexity are really quite interconnected. It's not just something, oh, I come up with an algorithm and then I have to come up with a trick that shows that my algorithm is best. No, what we're learning now is that actually within this vast world of algorithms and complexity, right, you can use elements from a certain area of complexity theory, which is very connected to algorithms that, you know, everyone wants to solve. And those, instead of being separate areas, they're actually quite related via all these reductions, right? So the idea here is that reductions, right? So reductions in computer science relate seemingly disparate areas of mathematics and computer science, right? So that's one thing that we learned, is that because of these reductions, we can see that these seemingly disparate areas of math or computer science, they're actually quite related, right? Because these are equivalent problems in the computational lens. And also, another thing that we learned is that even certain techniques like hashing and fingerprinting, they're highly used in interactive proofs, right? So these are really central techniques that they help us in many, many settings, right? So, and another thing that we didn't learn much in this course was that we can actually use, like, because I mostly emphasize now how complexity can help you in improving kind of hardness of approximation and so on. But if you think about it, this is also a kind of a paradigm that we can use algorithms to prove lower bounds, right? So in particular, for example, we learned how by getting interactive proofs, we can prove the PCP theorem, which is an algorithm, right? Which is say, oh, there exists like this proof system can actually solve all the problems from NP, right? So this is an algorithm that once we have this characterization, we're able to get hardness of approximation. So this is an instance of algorithms used to prove lower bounds. And recently, there is even a much higher trend that you can use a lot more algorithms to actually prove a lot more lower bounds, right? Which is really impressive. Okay, so this interconnectedness doesn't go only one way, right? It actually goes both ways, that better algorithms gives us lower bounds, and we can use many lower bound results to actually, say something about algorithms like hardness of approximation. Okay. So, all right. And again, as I emphasized before, and I cannot emphasize this enough, right? algorithms in forms of reductions, right? They're used to prove that even easy problems sometimes cannot be improved. Okay, and this is again like the fine-grained complexity. But as we saw, like these reductions are really, really key to relate problems in computer science or whatever problems you're trying to solve, right? Is a way of saying, oh, this problem is equivalent to the other one, computationally speaking, right? So this is kind of learning these reductions is essentially learning how, you know, mathematics or physics or, you know, everything algorithmically is interrelated, right? So, all right. And now this is the first part of the lecture. The next part is pretty short, but do you have any questions so far or any observations? Or let me pause the recording. So, all right. So now that we have learned so much, right? The idea is, where do we go from here, right? Well, all right. How can you learn more? And again, I said it before and I'll say it again. So, you know, if you want to learn more, I highly encourage you to take more advanced courses next term. And you can see, for example, the list of graduate course openings in this web page, or you can try some research opportunities at Waterloo, okay, because it's quite unique. We have a bunch of amazing faculty, and you should take advantage of us to, like, you know, experiment of what research is like, see if you like it. And it's a lot of fun, I can tell you. And, you know, if you're interested in doing research, you should just check all those opportunities for undergrads. And, you know, just go on all these web pages and see what research opportunities are available. And yeah. And now I want to talk about a little bit of philosophy in the end, right? Since this is the conclusion class. And the idea is, you may wonder, well, I learned a lot of theory. I did a lot of hard math, like these exercises were really, really hard. You know, and all this theory stuff is okay, but is it really useful? And the answer is certainly so, okay? And actually, lately, I may even dare to say that the gap between theory and practice has been quite short, okay? So, and it's not just lately, because if you think about how, you know, linear programming was developed, like the applications were right there and they were begging to be solved. And people have always studied computer science in a way that's very concrete. But even nowadays, like with zero knowledge proof that we learned, for example, that was, you know, introduced in the 80s, and now zero knowledge proofs like maybe took 10 years and 15 years. Now it's being applied like very, very much so in like throughout computer science, right? So this gap between theory and practice has become quite short. And for example, there's an intense use of theoretical cryptography and distributed computing in cryptocurrencies, right? Which are problems that before were like, oh, okay, these are just theoretical problems, but then they have found a lot of applications of a lot of theoretical results. Well, cryptography, we know, is highly used in e-commerce, and there are, you know, several algorithms nowadays are used in computational biology. And you know, Markov chains that we learned, they're, well, used in PageRank, which is an extremely important algorithm. And it's also used in simulations of physical systems, or also if you want to sample something, or if you want to count a certain number of objects, which appear quite a lot in real life applications. And there's many, many more applications. So this whole theory stuff that you learned, actually, you already have a lot of applications, right? And for example, even multiplicative weights update is used in learning theory, or is used in machine learning, in regret minimization problems, for example. So all of this theory stuff is not just pure theory. It's very useful and very concrete, right? And yeah, now I guess I'll open the floor to you. And if you have questions, I'm happy to just talk about them.